In the last video, we took a look at being able to use just the regular old Euler's method. Now we're going to take a look at something called the improved Euler's method, or Hume's formula. And essentially what we're going to do is similar to what we did with differentiation, where we did a forward difference. That's exactly what we're going to do here, is we're going to take the average of the current iteration and the next iteration. And we're hopefully going to get a more refined approximation at the point. All right, so it's not a centered difference, it's not a backwards difference, it's just going to be basically just taking the next iteration and averaging them out. Now, the good news is for the problem that we're going to be doing, we are just going to utilize the same exact code as we did for the last problem, except we're just going to change this algorithm, because notice in the problem that we're asked to do, we're just using the same exact differential equation, the same exact initial condition. We're using the desolve function, which we did before, and we're just approximating the same value using the improved Euler's method. All right, so here's what we're going to do. So this was the code from before. This is all going to stay the same. Nothing's going to change because that's the exact solution. This is all going to stay the same because that was the previous, and I'm just going to compare it. What I'm going to do is I'm just going to cut and paste all of this. All right. I'm also going to put in an fprintf to just make sure we have a couple lines separating the previous and the next algorithm. All right. And the only line of code that we're going to change is this one right here, the next y. All right. Everything else is going to be the same because we haven't changed anything. We're still outputting the same parameters except for the y estimate. So we just need a new next y. Let's look at the algorithm. The algorithm says that we're going to take current y plus h over 2 times this mess. So let's just get that out of the way first. So we're going to have the current y, which we already have, plus h over 2 times. All right, so this is where it gets a little sneaky. All right, so I'm going to separate this out so that way we can kind of focus on it as we're doing it. And then I'll bring it back together. Now, the first thing we notice is that we are going to evaluate the function, right, at the current points. So that is going to be our 4 times x1 minus 2 times our current y. All right, so that takes care of this. All right, so this is going to be our fx naught y naught. All right, now to that, this is where it starts getting a little uglier. We're going to go ahead and take the function and evaluate that at the next x. So that's going to be plus 2 times x1 plus h. All right, so that's our next x. That should be 4, excuse me, not 2, because the function was 4x minus 2y, minus 2 times our next y value. All right, so that's going to be current y plus step size. That's current y plus h times, and it's going to be h times the function itself. All right, so that means we're going to take 4x1 and then minus 2 current y. All right, so that's going to be 4 times x1 minus 2 times current y. All right, so close that parenthesis, close this parenthesis, and then close this parenthesis. And then finally, we have the one from the very beginning. All right, and that closes all of them out. All right, now, moment of truth is if we coded this correctly. All right, so when you're doing it, you just have to be really careful as you're going through. All right, so let's run it. Invalid use of operator in 37. Let's see. Oh, right here, there's a period. Not sure how that got in there. All right. All right, so we still have a little bit of error going on with this. All right, in fact, more than suspected. So I'm going to check the code real quick just to make sure I didn't make any errors or anything like that. And right here, I can see right away that I put a multiply instead of a minus. All right, so let's try that and see if we get a little bit better result. All right, there we go. All right, so this was the original Euler's formula that gave us about a 10% error. All right, using the improved Euler method, we end up with just about a little less than a 1% error. All right, and we probably saw that, if you remember, by utilizing some of those improved methods for differentiation, we were able to get a little bit better approximation, and the same thing happens here with the improved Euler's method. All right, so the good news is that even though we're using a more complex algorithm, we can average out the current and the next iteration to be able to get a much better approximation than what we did with just the regular old Euler's method. All right, now the last type of algorithm that we're going to look at is going to be a Runge-Kutta method, and that's actually going to be hopefully better than the improved Euler's method, but again, at the expense of improved accuracy, we're going to see that the algorithm is longer.